Dear audience, let me introduce you our next speaker, Matt Brems, who is managing partner and principal data scientist at BetaVector. And Matt will tell us about good, fast, cheap, how to do data science with missing data. Matt, microphone is yours. Go ahead.
All right, thank you very much, Ross, and thank you everybody for joining. Like Ross mentioned, my name is Matt Brems. I use he, him pronouns. I'm based in Baltimore, Maryland in the United States, and I'm here today to talk with you about missing data. As we get into this, I'm going to go ahead and share my screen. There's a link that you are welcome to use, and it will take you to my GitHub profile. So I'm happy to drop the link here in the chat on Zoom. I recognize that not everyone may have access to the Zoom chat. So I will also show it on the screen here. Go ahead and click present. All right, so with today, I'm going to have I'm snoozing my notifications as well so that those aren't distracting to you. So today, you're welcome to head to the site if you would like. It is not obligatory, but if you're interested in more content, I've got links, I've got Python code. You can head to this link, github.com/MatthewBrems/missing data short version. This is going to be a condensed version of a longer talk that I often give about how to do data science with missing data. So feel free to check out that link. If you check out that link, you'll notice a few different pieces of information here. First, in the README, there are a lot of links that you are welcome to check out that may help you to better understand missing data if you want to learn beyond what we talk about here. There are also 3 Jupyter notebooks that include code. We're not going to walk through that today in the interest of time, but you're certainly welcome to take a look at it if you've got a Python background, or even if you don't. The goal is for you to be able to take a look at it and understand it as best as possible if you would like to do so. The last thing, if you want to follow along with the slides, you can click missingdataslides.pdf and you will see a PDF version of the Google slides that I'm sharing now. So feel free to go ahead and take a look at that if you would like to do so. With that said, I'm going to go ahead and dive in because we don't have a ton of time together today. Again, you're welcome to take a look at this link for those who had just joined, but you do not have to if you would just prefer to follow along here. With that said, let's go ahead and get started. So our talk, good, fast, cheap, how to do data science with missing data. I'm not going to spend a ton of time introducing myself. As Ross mentioned, I'm managing partner and principal data scientist at BetaVector. I'm part of the distinguished faculty at General Assembly, and I volunteer with Statistics Without Borders on their executive board as a marketing and communications director. My data science background spans a bunch of different industries. I did work at RoboFlow, which focuses on computer vision. I've worked in finance, I've worked in education, in politics, in consumer packaged goods, in addition to the freelance data science work I do now at my data science consultancy. And one of the things that we're going to see is that across all of these industries, and I imagine in your experience as well, we're going to run into some missing data. So the big question is, how do we deal with that? So our agenda for the next hour or so, we're going to start by doing an introduction to missing data. We'll move very briefly through that. We'll talk about some strategies for doing data science with missing data. And then we're going to wrap up by talking about what are practical considerations and warnings for you whenever you're trying to apply some of these approaches that we're going to talk about. So jumping right in, how big of a problem is missing data? And one thing to note, for those of you who are on Zoom, if you're able to join via Zoom, that's wonderful. I will keep an eye on I will be sure to keep an eye on the chat to see if any questions come up. So with that said, how big of a problem is missing data? That's a really tough problem for us. And it's a really hard question to answer because practically speaking, we can only see what we observe. Now, that might seem like an obvious statement. We're basically saying we can only observe what we observe. But the that kind of begs the question. If there's a missing data point, we don't really understand how big of a problem that one missing data point is, or those two, or those three, or those four, because it's missing. So we can try and estimate how big of a problem that is. But realistically, one of the ways that we can try and answer this is to use simulated data to help answer this question. And at this point, I'm going to move over to the Jupyter Notebook, where we're going to be able to see this in action. So what I'm going to do is I'm going to pull up my Jupyter Notebook here. I'm going to open up the 0, 0 interactive plot. You're welcome to do this on your own. You don't have to if you don't want to. What I'm going to pull up here is I want us to be able to quantify the impact of missing data. So I'm actually going to go ahead and restart and run all of these. So right now, all of these should run as is. You should not need to change anything. All of the cells have been written for you. While that's running, two things that I want to call out. If I scroll all the way up to the top, there is a pip install line up here. You may or may not have all of these packages. So if you do choose to follow along, feel free to uncomment that first line. This, of course, assumes that you've got Jupyter and you've got Python already set up on your computer, which may or may not be the case. Again, if you don't have that, that's okay. I'm going to walk through this without you needing to run a single line of code. So as I scroll down here, we're generating some fake data for income and age. And if I scroll all the way down here, I've generated a scatter plot. This scatter plot, on the horizontal axis, I have age. On the vertical axis, I have income. And I have 100 data points here. Each dot that you see is one individual. Now, this orange line here represents the truth. That represents, if I'm a god, I'm an oracle, I know the true, real relationship between income and age. Now, generally, as data scientists, we don't have access to that information. Generally, what we do is we sample a bunch of individuals. So maybe we poll 100 people. Each of these dots represents one person. And then we build a line of best fit or some type of model. This blue line of best fit here is the model that we would build on that data. And notice that there's a gap between the truth that only an oracle, an all-knowing oracle would know, and our blue line, the blue line we've constructed. One note that I want to make here, some of these dots are blue and some of these dots are gray. The gray dots represent individuals where income is missing. So I don't have access to their income. So if you were to look at the data frame, you would be able to see a number of places where there might be NAs or not applicables, where that data is missing. So what I've got here, if you were able to run all of those cells, is you're able to play around with this slider and see how that blue line changes based on the percentage of data points that are missing. You can also change the type of missingness from missing completely at random to missing at random to not missing at random. Now, we haven't gone through these terms. We'll go through those terms a little bit later, but this is a way for you to be able to see as you change certain things and your data appears to be missing, how does that affect the predictions that you make? Now, I don't have the specific estimates written out here on the screen, but if I scroll back up to this scenario where my data is missing completely at random, and I'm only missing 20% of observations, that is 20% of those dots are turned off and they represent missing values. The difference here between the slope and the y-intercept of the blue and the orange lines is pretty significant. The difference in the slope between the blue and the orange line is actually is over 40%. And if we think about the y-intercept, where age would be equal to 0, that might not be a very interpretable thing for us. We generally imagine that somebody who is age 0 has no income, but the y-intercept itself is also, based on the scenario set up here, also off by over 80%. Now, that's a really, really big difference and something that we should be really aware of when we're working with data. So with all of that said, I want to move back to the slides where we were trying to answer the question, how big of a problem is missing data? Naturally, the answer to that is it depends, but we can use simulated data to try and help quantify how big of a problem missing data can be. And I would imagine that many of you who are tuning in today see instances in which you're missing more than 20% of your values. So what is a realistic approach for us? If you're not familiar with the good, fast, cheap methodology, what you can imagine are 3 overlapping circles like you see on the left-hand side. Generally speaking, when we're doing a project, our boss or our manager or our client wants us to be able to do a project that is done well, it's good, and it's done quickly, it's fast, and it's done cheaply or cheap. The problem is that good and fast and cheap, people tend to be dreaming. In project management and product management, we can generally do things that are good and fast, but they tend to be very expensive. We can do things that are fast and cheap, but they're not going to be good. Or we could do things that are cheap and good, but it will take time to deliver. In this case, it's not fast. So I like to apply this to missing data. When you're thinking about doing data science with missing data, there are a few different approaches you can take. I might describe, if you were to just drop all values that contain any missing data or all observations that contain missing data, or you do some sort of single imputation, and we'll talk about what that is. I would say your analysis is fast and cheap, but the downside of that is that your analysis is not going to be as good as it could be. If you do proper imputation or use the pattern submodel approach, you might have an analysis that is good and cheap. And then if you gather your data in a complete manner, so you gather all of that data up front and there's no missing data, it might be good, or your analysis would be good and it would be fast, but it's not going to be cheap. It often costs a lot of money to invest in order to gather that data in a complete manner up front where no data is missing. Now here today, I want you to be able to recognize the trade-offs of these. And in some instances, you might say that single imputation is okay. However, I would encourage you to think about what other options exist, and then you can advocate for yourself and for your project when you're working with clients or supervisors. So that's the intro to missing data. And now I want us to get into strategies for doing data science with missing data. I want to spend the majority of our time focusing on accounting for missing data. So I'm going to go through the avoiding and ignoring sections pretty quickly. Luckily, this is being recorded, so you'll be able to see this afterward. Avoiding missing data. It is often more expensive upfront, but cheaper in the long run to avoid missing data than it is for you to make guesses about how to best handle that missing data. That is, if you were able to design some data collection process that allows you to gather all of the data up front, then that often will pay off better in the long run, but it does require an upfront investment. Some things that you might do to try and avoid missing data. You might decrease the burden on your respondent. There's a number of restaurants that I frequent here in the United States. One restaurant is Chipotle, and one restaurant is Buffalo Wild Wings. And Chipotle often sends both organizations ask some customer satisfaction survey questions when I eat there. Chipotle sends it to me on my phone, and it's one question, maybe 2 questions if I'm dissatisfied. Buffalo Wild Wings asks 30 questions. Instead of them sending me a push notification on an app or something like that, they print out a receipt. I have to go to my computer, type in a long website. In addition to the website, I need to typing the web page address. I need to type in a 16-digit code, and then I need to fill out this 30-question questionnaire. That's a pretty heavy burden. I almost always respond to Chipotle's request for information. I almost never, or actually I have never completed, I've never completed Buffalo Wild Wings' customer satisfaction surveys because in part of the burden on me, the respondent, I'm giving them my data, and the asks that Buffalo Wild Wings are making is significantly higher or greater than the asks that Chipotle is making. Think about improving accessibility. Make sure that you're not removing part of the population by the design of any information that you're gathering. If things are only available on the internet, consider people who don't have access to the internet. If you're thinking about a phone survey, people who are hard of hearing may have a much more difficult time responding to that survey. This doesn't just have to be about surveys themselves, but it's a convenient vehicle for us to discuss this. Thinking about things on a screen, is there a way for you to ensure that things are accessible to people who may be colorblind or who are hard of sight or have any other issue that prevents them from being able to easily use a screen in that way? Think about changing the timing of your survey, maybe having a survey go on, perhaps don't just call people between 9 a.m. and 5 p.m. Monday through Friday. You're going to get a very specific population of people if you do that. Consider the content of your survey. If you incorporate things in your survey asking about income, or asking about drug use, or asking about things that might be sensitive topics, people may be significantly less likely to respond. And so that may cause you to find data that is missing. Or rather, when you look at your spreadsheet or your data frame of data at the end, you might notice that you've got observations for which you haven't observed certain values. You've got some missing data. And part of that can be driven by the content of your survey. So keeping these things in mind, I encourage you and your team to take steps toward avoiding missing data. Then ignoring missing data. So we can ignore missing data, and I imagine this is something that you and others may commonly do. By ignoring missing data, we assume that the observations for which we've observed data are similar to those observations for which we're missing data. And that's often not a great assumption for us to make. If we've got a very, very small amount of missing data, that might be a reasonable thing, or that might be an okay thing to assume, but this is an implicit assumption, and we need to be aware of those assumptions when we're trying to do some sort of analysis. So one very rough general guideline that I've heard in the past, people often say, well, what's a number? Give me a number at which we would be okay if we just ignored missing data. The rigorous answer is we're never okay ignoring it from an academic point of view or a theoretical point of view. Now, when it comes to working with practical data sets and working with time constraints and resource constraints and other things that may restrict what we're capable of doing or what we're able to do, we have to make real world decisions every day, and there's trade-offs associated with those. So a general, very, very rough guideline that I have heard is that we may be okay ignoring missing data if less than 5% of our values are missing. Now, there are, as always, some caveats to this. If you're tackling a supervised learning problem and you're missing a lot of your Y variable, the output variable, the thing you're trying to predict, this might be inadvisable. For example, if you have 20 variables in your data set and almost all of your missing values are from that Y variable, that thing you're trying to predict, that might be really, really bad. Even if it's less than 5% of your overall data, if you're missing maybe 50% of observations for Y, I personally would probably not feel very comfortable ignoring missing data, even though that threshold of 5% of your data, even though that threshold has been met. If you're missing a lot from meaningful variables as well, this may also be inadvisable. If there is a variable or two that you know, this is particularly important to what I'm trying to do, you may not feel comfortable ignoring missing data, even if you're still below that 5% threshold. Now, we're going to move into accounting for missing data, but I want to encourage you to shift your mindset before we do that. There often is this, and this is the belief that I had when I started learning about missing data. I had this belief that you could just plug the gaps in your data. We would just have some algorithm that would allow us to fill in the gaps. This is known as imputation. And we have to do this in a really, really specific way, or we're just making up data. In most cases, we're not fixing our data. We often think of that. We often think, I'm going to take the tools that I learned today during this session, and it's going to be one step in my data science process. And I'm just going to add that in maybe during exploratory data analysis. I add it in and then boom, everything is fixed so that I can proceed through the process as I otherwise would. But that's not usually how doing data science with missing data occurs. In most cases, we're not fixing data, we're just learning how to cope with it. That's why the subtitle of this talk is how to do data science with missing data. We're not getting rid of that missing data. We're not able to just magically wave a wand and make it go away. But we have to figure out how can we fit, or rather than fix, how can we do data science in the presence of missing data? So at this point, I want to move into accounting for missing data. And there are two different types of accounting for missing data that we need to be aware of: accounting for unit missingness and accounting for item missingness. So what's the difference between those? With unit missingness, it means that all values are missing from a given observation. So in this case, index 3, and in here, I think I'll pull up on a laser, so it's hopefully easier to see my mouse. Index 3, this person, we see an NA everywhere. So that would be an example of unit missingness. Item missingness, I like to call this Swiss cheese missingness because it's got holes in it. This is where some, but not all values are missing from an observation. So index 1, we notice that there's an NA for age, there's an NA for income, but their sex has been filled in. These would be examples of item missingness. Individual 2, or index 2, we see item missingness. Individual 10,000, we see item missingness. So the tools that we use to describe these differences here, the tools that we use are going to be a little bit different. For unit missingness, what we're going to do is something called weight class adjustments. Now I'm going to very briefly pull up this notebook so that you can see it. This is also in the repository. You're welcome to pull this up yourself if you would like. But what I'm working with is, let's say that you've got data. Let's say that you're an HR professional. I'll zoom in. And you've got data from two different departments. You've got a finance department and an accounting department. Now, you as this HR professional, you want to understand, what is your employee satisfaction? How satisfied are individuals in your company? Well, here you administer a survey, and I've got that called score here. So it's a value from 0 to 10, and you want to understand on a scale of 0 to 10, how happy are people to be working for your company? Well, there might be a difference between finance individuals and accounting individuals. Maybe at least in the United States, we might think of accounting individuals as they tend to be much more organized. Things can't fall through the cracks. They have to get everything done. They might be a little bit more responsible with completing everything. Finance individuals, on the other hand, not to say that they're not responsible, but they might have too much going on. They may have a lot of higher priority things, and maybe responding to an HR survey or a human resources survey isn't worth their while, in their opinion. And so we might notice that there are different rates at which the finance and the accounting team might respond to their surveys. So I've created some data here that shows that. So we've got a finance and an accounting team that are split evenly. 50% of my people are in finance and 50% of my people are in accounting. But then we administer the surveys, and what we do is we notice that 77% of the responses came from the accounting department, meaning only about 22 or 23% of our responses came from the finance department. This technique, called weight class adjustments, will allow you to calculate a weight for each observation. And again, you've got all of these resources, so I don't want to focus too much on this here, but you've got a weight that you can calculate for each observation that basically changes the weight of each vote. So using this formula, we see that the weight for each accounting vote is 0.645. So we might take every single person who responded in the accounting department, rather than their vote or their survey counting as one survey, instead it counts as 0.6458 surveys. So their vote gets reduced a little bit. On the flip side, looking at the finance team, because there were fewer finance responses, the weight for each finance vote following the formula above is significantly higher, 2.2. So for every one survey that we received from a finance individual, that survey actually weighed at 2.2 surveys. If we were to combine the weights and the number of responses, we see that we get the same number here. There's a floating point arithmetic error here, but we see that we get a net 2,768 responses from each of those departments after accounting for those weights. So why does this matter? If I were to calculate the average employee satisfaction score, I would get 5.7 out of 10. If I calculated the weighted average, so taking into account those weights, we see a pretty significant drop here, 0.3 points down. So we go from 5.7 down to 5.4. And maybe that's because finance people, on average, in this hypothetical scenario I've created, are less happy on average. But if they also tend to respond less to those surveys, that might be hidden if we just look at the average employee satisfaction score. So here, by taking into account that weighted mean, we're able to see a difference there. There are some downsides to this approach. Our goal here is to decrease bias. For those with a data science background, you know that oftentimes when we decrease bias, we increase variance. And so we need to be aware that we do not want to increase variance. There's a good article in the New York Times about how polling averages were skewed by one individual who got a very, very, very large weight in a survey. His weight was, I think, 300 times larger than the smallest weight in the sample. So this one individual really dramatically skewed polling estimates in the 2016 political cycle. Something else to take into account here, this is only available if you know that true underlying distribution. As an HR professional, I would probably know how many people are in finance and accounting. However, in many cases, we won't actually know that true distribution. So you may need to make an educated guess about how many people are in each group if you're trying to especially forecast something forward, like in a political context, for example. In Python, there are, and in R, but I've written this in Python, there are ways to build a sophisticated model that take into account the weights. So there are ways to do like a weighted random forest or a weighted least squares regression model, if you would like. This technique is called weight class adjustments, and it's something that you may want to be aware of when you're dealing with a situation where perhaps people don't respond to a survey at all, but if you've got any supplemental information about them, you would be able to use that supplemental information. I'm going to go ahead and close this notebook, and I'm going to move back to the slides. So I want to pull all of these pieces together in a workflow, and I'm going to recap this workflow once we get through the item missingness part. So if I'm tackling a problem and I notice that there is data that's missing, the first step that I take is I try to evaluate how much missing data I have during my EDA or my exploratory data analysis process. And is it worth my time to try and address this? If the answer to that is yes, if I've got the time and the energy and the ability to do so, I say, yes, it's worth my time to address this. Then I move down to step 2. Is it reasonable to attempt deductive imputation? We're going to talk about deductive imputation in a minute. Then if there's still missing data, then I'm either going to go to 3A. If I want to generate predictions, I would use the pattern submodel method. Or B, if my goal is to conduct inference, then I try to use proper imputation and I combine my output using Rubin's rules. So with all of that said, I'm going to go ahead and let's get into some of these terms that I use that we're not familiar with. One is when I showed you that example of the simulated data and that line that moved as I changed some of the settings, you saw acronyms MCAR, MAR, and NMAR, and I want to walk through those here. So one type of missing data is called data that is missing completely at random, or MCAR. So let's say I'm a grad student in a lab and I'm pipetting. I'm taking solution from one place and I'm putting it into a petri dish, and I'm doing this over and over again. While pipetting, I reach for my pen and I accidentally knock one petri dish onto the floor. From that, and maybe the lid pops off. From that petri dish, I lose data that I would have otherwise collected. So for example, I'm looking at how much bacteria there is on day one, or the width of the bacteria on day one and on day two. And I'm recording all of this information. But down here, there was one petri dish, 11 millimeters of bacteria on day one. On day two, I've got a red line through that. That's missing data. It's contaminated. I can't use it. We would call this missing completely at random. The data of interest, the data that I'm interested in here, is not systematically different between missing data and observed data. What that means here is there's nothing special about that one petri dish that got knocked off. It wasn't like this petri dish happens to have so much more bacteria and that's why it got knocked off, or something else. That's not the case here. It was just totally at random that petri dish got knocked off. This is the best kind of missingness to deal with, aside from no missingness. The next scenario is data that's missing at random. And I'm going to pause here for a moment. I apologize. I'm simply the messenger here. I'm not the I'm the messenger. I did not create the way that these are titled. I think that missing at random and missing completely at random is maybe not the best way to describe this, but this is the terminology that others have set out before us. So we can have data that's missing at random. So I work for the Department of Transportation, and let's say that a sensor on the Pennsylvania Turnpike broke. The Pennsylvania Turnpike is a toll road, or a road or a highway that you have to pay money to be able to use. And let's say that there's a sensor that looks kind of like a camera that is counting the number of cars that go through a given lane. Let's say that sensor broke and we didn't gather any information from 7 a.m. to 10 a.m. on a given day. We would call this missing at random. Over here, we see time and the number of vehicles. And notice that the number of vehicles at 7, 8, and 9 a.m. is not recorded. It's in red, and I've got a slash through them. I've got numbers under there, but we actually wouldn't be able to see those numbers. As data scientists, this is just missing data that I don't have. We call this missing at random. What missing at random means is that conditional on data we have observed, the data that we're interested in is not systematically different between what's missing and what's observed. Put another way, whether or not a data point is missing depends on observed data. Here, I have observed time, 4, 5, 6, 7, 8, 9, 10. That's something that I have observed. I know that. The number of vehicles here, that's something where I don't know what those values are, but I can use time as a factor to try and help figure it out. So for example, time at 7, at 8, at 9 a.m., I might not have data for that on this day, but I can use data from other days. I can use estimates from what it looked like at 6 a.m. and at 10 a.m. to try and fill in those missing values. So conditional on data we've observed, that data of interest is not systematically different between what's observed and what's not. The last example here is NMAR, or not missing at random. This is the trickiest kind of missing data to deal with. Let's say, remember earlier I was talking about content in a survey. Let's say that I administer a survey with a question about income. Those who have lower incomes are less likely to reply to the income question. We call this not missing at random because data that's missing versus data that's observed, those are systematically different. Whether or not an observation is missing depends on the value of the unobserved or the missing data itself. So for example, here on the right-hand side, we see income, and we see that some people did not share their income. Notice that those incomes on average tend to be lower. It's not a perfect relationship. Someone making $62,000 did not share their income, someone making 50,000 did share their income, but this is not missing at random, where whether or not that data is missing depends, at least in part, on the value of that missing thing itself. That's really, really tough because it's missing, and the reason it's missing is based on the value of that missing thing, but we don't have the value of that missing thing because it's missing. So it's really, really hard to try and diagnose this and identify when it's happening and figure out how to proceed. However, we can do this. So a couple of things. One, there's a few different types of missing data, and we want to be able to understand what type of missing data do I see. The first example is Little's test for MCAR or MCAR. This is a hypothesis test. It's similar to students' t-test. The null hypothesis is that the data is missing completely at random. The alternative hypothesis is that data is missing at random, and you run this test, you get a p-value, and based on that p-value, make a conclusion about, is your data missing at random, or do you not have enough evidence to conclude that? One caveat is that there's no empirical test that exists that can evaluate whether or not your data are not missing at random. So really the only two options here would be missing completely at random, missing at random. But unfortunately, there's not a possible way here to determine, is your data not missing at random? Another technique that you can use to try and figure out what type of missing data you have is to take your data set and split it into two sets. One where your variable is observed and another where your variable is missing. So for example, let's say that I had a bunch of data and in some of my data, income is observed, and in other data, income is missing. What I do is I take my data frame and I split it based on where income is observed and where income is missing. Then I want to see, are there patterns in other variables? So for example, maybe I pull up a histogram of age for the income observed data, and I pull up a histogram of age for the income not observed data, and I look at those two histograms on top of one another, or I compare them. Is age significantly different here based on people who did and didn't report their income? If we see that, for example, age tends to be different or age tends to be lower where income is missing, that might suggest that my data is missing at random, where age is part of what's determining income and where age is determining whether or not income is missing. And then finally, just think about the missing data process. Can you come up with a reasonable theory as to why data is missing according to a certain pattern? Can you think this is sensitive content, or I only did one phone call, or I did an email survey, but it might have gone to the spam box? Is there a way for you to come up with a reasonable theory about how missing data came about? Based on that, and all of these here, you can try and understand, is my data missing completely at random, missing at random, or not missing at random? Which brings me to probably one of the most interesting parts of what we're going through here. How do we account for item non-response? Again, that's that Swiss cheese non-response. There are 5 techniques that I'm going to take you through here. We're going to, again, in the interest of time, go through these pretty quickly, but we'll be able to summarize each of them. The first is deductive imputation. In deductive imputation, you use logical rules to fill in missing values. So maybe a survey asks if the respondent was the victim of a crime in the last 12 months, and the respondent says no. Then the survey asks, was the respondent a victim of a violent crime in the last 12 months? And the respondent leaves that answer blank. Based on logic and rigor, we can fill in that missing value, because since the first answer was no, the second answer must logically, definitively be no here. So some of the considerations here, this requires specific coding. It's not like you can just develop a Python package that will automatically know that. It requires you to know your data well enough to understand those logical relationships. It can be time consuming. It does require no inference, which is really good. And it can be used regardless of missing this type. So whether your data is not missing at random, or it's missing completely at random, or it's missing at random, you can use deductive imputation. So that's one technique. And if, as you may remember in the workflow, this is my recommended first step when you're trying to fill in missing values or when you're trying to do data science with missing data. If you've got time, I encourage you to try doing deductive imputation. Then mean, median, or mode imputation. So for any NA value in a given column, you can replace your NA or your missing data with the mean or the median or the mode of your observed data there. Some considerations. This is quick. It's very fast to be able to do this. It's very easy to implement. It seems reasonable. If I've got missing values, the likeliest thing it's going to be is probably the mean or the median, right? Maybe the mode. It can significantly distort your histogram and underestimate the variance in your data. And I'll talk about why that's a problem in a moment. It should also only be considered if your data is missing completely at random. So this is an example. So up top, we have a real histogram of age. We see roughly a uniform distribution between, I think it's 20 and 65 years of age. Now, if let's say 30% of that data is missing, down below, we've got the data that's observed and imputed. This orange bar resembles the imputed data. That's really different. That orange bar, notice that really distorts our histogram. Now, the average of our data is going to stay the same, but some of our other statistics might really be off. Specifically, our standard deviation and our variance. So, speaking of standard deviation and variance, on the next slide, there's going to be a formula or a few formulas. I know that might be jarring to see. I will walk through exactly what it means, but just wanted to know you're going to see the standard deviation formula on the next slide. So why would underestimating variability in our data be a bad thing? Here, I've got S, or sample standard deviation, and I've got the definition of sample standard deviation for K observed values. So let's assume you've got a data frame of N observations. Your first K values are observed. K plus 1 all the way down to N, the bottom part, is not observed. Well, the sample standard deviation, if you calculated that sample standard deviation for K observed values, this is that formula. Let's say I wanted to rewrite that formula for N values, all of the values in my data set. And let's assume that we imputed values here. Let's say we imputed all of our missing values with the mean. Now, we see this is the definition of standard deviation for N observed values. We're dividing by N here, and we're summing all the way up to observation N. But I'm going to rewrite this. I'm going to take this sum here, and I'm going to break it out. First, let's look at the first K observations. These are all of those observations for which we've observed our values. K plus 1 to N, the bottom part of my data frame, remember, that's what was missing in this scenario. So given that that's missing in this scenario, I filled in the mean. So instead of putting just xi, the value of that observation, I fill in the mean. Well, that means here, the mean minus the mean, that's 0. 0 squared is 0. Summing up a bunch of zeros is still 0. So this whole thing here that I'm mousing over, that can go away. That's just 0. So if I remove all of those zeros, this is what that formula ends up being. We're summing all of our observations and their squared distance from the mean from I equals 1 to K, those first K values, but we're dividing by N, which is larger. What this does is this artificially reduces our standard deviation and our variance. Why does that matter? Well, how do we use standard deviation and variance? We use standard deviation and variance when we are calculating p-values. and generating confidence intervals. If we underestimate variance in a confidence interval, we're going to have that same level of confidence, maybe say 95% confidence, but that confidence interval artificially gets smaller because we shrink our standard deviation. So our results look more precise, but it's literally only because we imputed the mean. If we underestimate the variance in a hypothesis test, that p-value itself is also artificially going to get smaller. So our p-value might normally be 0.08, but after imputing the mean, maybe it goes down to 0.04. Well, that p-value just went from insignificant to significant. We might make conclusions because we filled in the mean. So the mean or the median or the mode, those seem like very reasonable things to do to fill in, but there's actually a lot of downsides to those. So underestimating variance can be very bad, especially if you want to do any sort of inference. So what we want to do is find an imputation technique that does not underestimate variance. Here, if we were to impute the mode, we see a similar sort of thing where the mode just is over here. So we get a very large bar here. So this almost is worse than mean imputation. So oftentimes people will say, what if we try something like regression imputation? So let's say that you're missing income for some people and you've observed age and the highest level of education for everybody. Maybe what you do is you build a model in your data where your X or your input variables would be age and the highest level of education that people have. And your output, Y, is income. And you fit a model, maybe like a line of best fit or something else. For any NA value in your original data, what you would do is you would replace NA with the predicted value from that regression model that you built. So you would use regression to fill in those missing values. And that seems reasonable, and it's probably going to be better than mean or median or mode imputation, but it will still distort your histogram and underestimate your variance. Here we see an example of that. Notice that our orange imputation bars, those are more spread out. It's not just one bar right at the mean or the median or the mode. It's more spread out, but it's still clumped there toward the middle. So when it comes to single regression imputation, that's also not going to be the ideal output. Here, what you see on the left-hand side, you're seeing what is known as deterministic imputation, and that's exactly what we described. If I created a line of best fit and filled in those values, all of those values would be exactly on that line. It's deterministic. However, we can better model the spread, better model the variability in our data by adding in randomness to that. Notice that the black dots over here look to be more representative of or better reflect the little gray dots, the broader population that we're trying to describe. So that those random imputations will better capture the range of data that we're working with. So we want to include some sort of randomness, which brings us to proper imputation. In order to properly impute data or fill in those missing values, we need to fill in missing values, understanding the proper amount of certainty and uncertainty we have in a given position. Replacing an NA with one value treats things like we know definitively what that value is. If there's a missing data or missing value and you plug in a value of 4, you're effectively saying, I know definitively that this value is 4. But that's not true. We need to impute multiple times. And I'll show you what this means. We're going to make many copies of our data set, say 10 different copies of our data set. We're going to use random regression imputation to generate a value for each NA in our data set. So we're going to fill in each NA in each data set. Once each of those 10 data sets are complete, or however many data sets you build, you're going to do your final model, final analysis on each data set, and then we're going to combine the results of our models together. And I'm going to walk through this step by step to show you what I mean. This is a data set here. I've made this data set up. Step one is to make copies of that data set. Those red X's represent NAs, or missing data, and I want to fill all of those in, but respecting the right amount of variability I have in these data points. So I create a copy of each of these data sets. Step two, I'm going to build a model or multiple models for imputing. So maybe I want to use this first column where I've observed all of my values. I want to use that to build a model to predict what this X is going to be. I want to do the same for all of my columns of data. So you build models for imputing those missing values. Then I'm going to impute those values properly. So I'm going to use that model to fill in this X. So in this data set, remember that we want to add in some randomness. In this data set, I fill in a 6. In this data set, my model generates a 7. And in this data set, my predictive model fills in a 6. Notice how these values vary a little bit from each copy of the data set to one another. The purpose of this is not to have one data set, but rather to be able to say all of these values, I don't know if this is going to be a 5 or a 6 or a 7, but we want to model the amount of variability we think we might have in this data across all of those missing data points. Then what I'm going to do after I've filled in those missing values is I'm going to build my final model on each data set. So let's say my goal was to fit a line of best fit. Rather than doing that on one data set, I'm going to do this on all in this visual 3 data sets. So I build one linear regression model here on that first completed data set. I then build a second linear regression model on that second completed data set. And I build a third linear regression model on that third completed data set. So that's step 4. Then what I need to do is I want to combine those models together. If I'm generating predictions, what I'm going to do is I'm just going to average those predictions together, or I'm going to pick the plurality class, the likeliest class. So if I go back here, let's say that I'm trying to predict this Y variable. And let's say once I've built these 3 models, I've got a new test observation. And let's say in this top model, I see that I predict that Y is 10. In this next model, I predict that Y is 15. And in this next model, I predict that Y is 10. Well, I take 10, 15, 10, and I average those to get 11.6667 or 11.6667. That's the average prediction of those 3 models. It's almost exactly like how, or it is exactly like how a random forest works, where you've got a bunch of different trees and then you just average those predictions together. That's how we would make a decision here. If your goal isn't to do predictions, but your goal is to do inference, understanding how X affects Y, there's a set of rules, and I've got documentation and links in the repository for this. There are tools called Rubin's rules that will allow you to combine, I'm going to go back to the previous slide, slopes and y-intercepts. So you've got beta naught, gamma naught, and delta naught as 3 different y-intercepts here. Rubin's rules will tell you how to aggregate those together to be able to get a confidence interval for each of those estimates. Same with the different slopes in your model. Again, they're called Rubin's rules. So we've gone through 4 different methods of imputation: deductive imputation, mean median mode imputation, single regression, and proper imputation. The last example I want to go through here is the pattern submodel approach. Big picture, we're going to take our data set and we're going to break it into subsets based on missing this pattern. Then we will build one model on each subset, creating many different models. So here on the left-hand side, I've got some data, Y, X1, and X2. Y is completely observed, X1 and X2 are partially observed. I'm going to start by breaking our data set into subsets based on missingness patterns. So here, where I've observed all 3 values, that's one subset. This next tier where I've observed Y and X1, but not X2, that's a separate subset. Down here where I've observed Y and X2, but not X1, that's a third subset, and so on and so forth. Then I'm going to build one model on each of these subsets, creating many different models. So up top here, I build a linear regression model, and it doesn't have to be linear regression. It could be a random forest or something else. But this linear regression model, Y equals beta naught plus beta 1x1 plus beta 2x2. On the next subset, I build a model here, Y equals gamma naught plus gamma 1x1. Notice there's nothing for x2. And I'm going to do the same for so on and so forth throughout the rest of my data. So I break our data set up into subsets. Then I build a model on each of those separate subsets. That's it. This is the pattern submodel approach. We never combine those models together. We just have, in this case, 4 different models that we would use for prediction. So some of the considerations of using this approach. When data are not missing at random, the pattern submodel method is expected to be better than imputation methods. When your data are missing completely at random or missing at random, the pattern submodel method has been shown to perform about as well as imputation methods. So for my money, if I want to do predictions, I'm going to use the pattern submodel approach. It does not require missingness assumptions. We're not making any assumptions about how our data are missing. If I go back to the previous slide here and we look at this second model, we've got Y, X1, but not X2. I just build a model with Y and X1. I don't need to make any assumptions about why X2 is missing. I don't have to make assumptions about how to fill it in. I don't have to make assumptions about is X2 missing at random or not at random or completely at random. I just don't make any missingness assumptions and instead build a model on the data that I've observed. You can generate predictions for test observations containing missing data. If instead, let's say that you did an imputation approach where you did fill in all of your missing values in some way or another. If you've got a test observation that has some missing values in it, you then have to fill in that test observation's missing values with estimates, then put it into the model. Here, with the pattern submodel approach, you don't have to do that. You can just, if there's a test observation that contains missing data, you just match it up with the corresponding pattern of missingness and fit it into that model. The downside here is that this is not a well understood method for inference, this pattern submodel approach. So that brings me back to how to pull these pieces together in one workflow. And the way that I tackle these problems are I start by saying, 1, how much missing data do I have during my exploratory data analysis process? Is this worth my time to try and address it? Maybe yes, maybe no. If yes, then I move to 2. Is it reasonable to attempt deductive imputation? And if so, do deductive imputation, where I use logical rules and relationships to fill in as much missing data as I can without making any guesses, all rigorous logic. Then I decide, do I want to generate predictions or do I want to conduct inference? If my goal is to generate predictions, I use the pattern submodel method because it tends to be better than imputing. If I want to conduct inference though, I'm going to use the best imputation method available. And if I'm doing proper imputation, which I strongly encourage you to do, I'm going to combine my output and my results using Rubin's rules. So I know that that was a ton. I just walked through the 3 different types of missing data, 5 different ways of handling missing data, talked about some of the considerations here now to pull this together in one workflow. We're almost done, and I know we're coming up on time. I want to wrap up with 3 practical considerations and warnings for you as you think about how to go about this. Warning 1. If your goal is just to get a complete data set for further analysis, you need to be very careful. What I mean by that is if you've got missing values and you just plug them in because you want to have a complete data set to hand off to someone else, you need to be really careful. After you construct that data set, if you fill in those values in R, in Python, in Excel, nobody will know what data is observed or what data is imputed unless you take care to make sure people know that. The second you give that data set to someone else, they may just assume that all of that data was observed, that none of it was missing. So that's really, really tricky and can be quite risky. So that's one thing. The second warning, improper imputation, like just filling in the mean, it is effectively making up data, which I believe is an unethical thing to do, and you should avoid doing this. Proper imputation, on the other hand, is not making up data, because we're not taking our NA and filling it in with one value as if we definitively know that value. Proper multiple imputation is going to impute data while properly estimating the amount of variance or that variability in your data. You're not going to underestimate the variance in that data. So I would encourage you to not do improper imputation, because at the end of the day, it effectively is making up data. And then the last thing, if you use Python, so you can use R, you can use Python, I'm sure that you can use other platforms to be able to work with missing data. R, in my experience, is much better for working with missing data. Python tends to, especially when it comes to the more statistical side of things, tends to require more. The Python has not yet caught up to R, in my experience, in terms of its ability to handle more rigorous statistical calculations. R is just designed for that. Python is catching up, but still, in my experience, not there yet. So there's some scikit-learn methods or sklearn methods in Python that are new-ish and can be used. So there's single imputer and there's iterative imputer. And these are designed to be able to help you fill in missing data. Iterative imputer was recently experimental. I believe it only came out about a year ago. So it was experimental recently. I think that a lot of the kinks have been worked out, but proceed with caution. These, and really any code, but in particular this code, may not work as expected. So you want to be very, very delicate and cautious when it comes to using this, and be aware of what are some of the limitations in everything that you're doing. So this brings me back to the end, talking about some of the trade-offs and the warnings and everything. What is a realistic approach for you when it comes to doing data science with missing data? You can go the fast and cheap route. You can go the good and cheap route. You can go the good and fast route. I would encourage you to focus on being as good and as cheap and as fast as you can be. But I especially consider you to focus on having an analysis that is good. There are trade-offs when it comes to working in the real world. It can often be difficult to convince a boss, to convince a manager, to convince a client that you need more time or that you need more money in order to be able to do something that is good. People often want things fast and want things cheap. However, given what we talked about today, I encourage you to be aware of those trade-offs. And so avoid single imputation where you can, avoid dropping all rows that just contain missing values as well, because those have their limitations. With that, thank you all so much for your time and attention. I have not seen any questions in the chat, but I'm very happy to answer questions that people have. Ross, you're welcome to come on and help as well if you want. But thank you so much for your time, for your attention, and for participating in the talk today. Thank you.
Thank you. Thank you, Matt. I do not see any question in Telegram chat and do not see any question on broadcasting link, but maybe there are any question by voice. Does anybody has a question?
Thank you, Matt. It was an awesome talk. And I have a question about the idea. We have a lot of instruments, we have a lot of tools to get insight about the code quality, like a code climate, like a sonar, like different analyzers, static analyzers. And what do you think about the viability of idea to create some kind of such tools for data? And is it reasonable and is it possible?
So I'm not familiar with those tools specifically. Could you describe those tools a little bit more?
Yeah, okay. This tools is about creating some kind of analysis about is this code good or is this code have some problems, and detect some insights about how we can improve the code level. And for data, I believe that we can create some kind of analyzers that can uh, get us inside, like about the missing data, but not only based on missing data, about data curation at all. Provide the data scientist with some insights about what kind of methods of imputation, of augmentation can be applied, and some kind of automatic exploratory data analysis, but a bit in deep.
Yeah, so I think that you certainly could develop tools that would allow for automatic exploration of data, and plenty of those tools already exist. You could develop tools around evaluating the accuracy and the consistency and the reliability and everything of your data as well. And those also exist. There are packages out there that make it easier to understand how much missing data you're working with. There are packages that and no code and low code tools that can just be easy for people to use to assess what's going on in your data. With that said, I do think that one of the biggest challenges, especially when working with missing data, is understanding what your data is telling you. And really, this is a data science thing at large. I think that it is very important to know enough about how your data is working, to have subject matter expertise, to be able to understand how is this data working, how is the data working, how do the things relate to one another? Like, for example, deductive imputation. I'm not 100% on this, but I think it would be very challenging, and maybe we'll get there at some point, but I think it would be really challenging for a computer to be able to automate fully the deductive imputation process, where it can automatically detect what are those relationships that exist in the data, the deterministic relationships in the data, and then use those to fill in. At minimum, I think a computer could flag those and say, we notice that this variable is always less than that variable, or something like that. Then from there, be able to flag that for a human. But I think that those sorts of tools would almost always require human oversight, especially when it comes to something like deductive imputation. I also think that when it comes to understanding what type of missingness you're working with, there's not a clear-cut answer as to, it's not definitively observable from where you are. So I think a lot of that also involves just human knowledge, human intuition, human understanding of data. So I think that there are tools out there that already exist that can help. I am confident that other tools can be built, though I'm not certain how rapidly those tools in the context of missing data are being built. I also think that a human is integral to that process, specifically a human understanding of that data.
Thank you a lot for your answer. And what kind of tools do you usually use for such kind of processes?
Yeah, so the tools that I generally use largely are going to be R and Python. I use SQL to gain access to data. I will sometimes use Tableau to visualize data. I use Excel and Google Sheets to open data up. I don't do a ton of analysis in there, but I use Google Sheets for tracking plenty of things. So yeah, I think that, so I use a variety of different tools, but largely it's, I have historically stayed away from those automated tools that detect things for you, and spend most of my time in R, in Python, and in SQL.
Thank you.
Yeah, of course.